In this video, we'll go over the answer key for Tuesday, April 14th. And what we're talking about here is quantum mechanics of an atom. Basically, that means what do the electrons around an atom look like? Traditionally, people thought of an atom like they do the planets. The sun's in the middle, which would be your nucleus, and the planets go around in a ring. So people used to think that electrons went around in a ring too. That's not true. What the electrons do is that they have a cloud, and basically electrons are so small and fast we can't tell where they are in this cloud. All we can say is that, for example, in this shape there's roughly a 90% probability that we'll find an electron somewhere in here. We don't know where it is, but we're fairly certain it's somewhere in here. And these shapes, we call them angular momentum quantum numbers. And we also use the letter L. Now, these shapes and the L numbers, so every L number tells you a different shape. So first, let's just look at the shapes and give them letters. So we have three letters to choose from: S, P, and D. So when we're looking at an electron cloud that looks like a figure 8, that is a p orbital. If it looks like a sphere, that is an s orbital. And if it looks like two p orbitals combined in this cross pattern, that is what we call a d orbital. Now there are some rules that go with our quantum numbers. So the quantum number n, that's like your most important quantum number. That tells you what energy level you're at. So n can go from 1 to infinity. L is our shapes we just talked about. And L ranges from 0 to whatever n minus 1 is. So you need to define your n before you can define your L. M sub L, you can think of that of ways we can orient the L. Let me just go back to the previous slide. So you can see we have our p orbital and it's on the z axis here. We could have our p orbital on the y axis, or we could have our p orbital on the x axis. That M sub L is just telling us what direction in 3D space is our orbital pointing. And the rules for M sub L is that it can have any number between plus L and minus L, as long as that's an integer, and that includes 0. So the question is, if n equals 4, what are my possible values of L and M sub L? So let's just start with our lowest value of L and move our way up to n minus 1. So if L is 0, M sub L could be 0. If L is 1, M sub L could be negative 1, 0, or 1. If L equals 2, M sub L is minus 2, minus 1, 0, 1, 2. And if L is 3, M sub L could be minus 3, minus 2, minus 1, 0, 1, 2, and 3. Alright, so what do these energy levels mean? What do these orbitals mean? So when we talk about orbitals, we're going to list them like this, like 2s. So the 2 is the energy level n, s is our L. So s has an L value of 0. So this is really n equals 2, L equals 0. A 3s would be n equals 3, L equals 0. So what's closer? The lower the value of n, the closer you are to the nucleus. That's what n's kind of telling you, so 2s is closer. Alright, so based on the rules we just talked about in the last problem, what set of quantum numbers cannot specify an orbital, or cannot specify a place where you find electrons? That's C. So here we have n equals 3, L equals 3. That can't exist. L has to be lower than n. So that is a fake orbital. C. Of the real orbitals, in question 2, which is closest, which is farthest? So the closest would be A, and the farthest is D. Again, where I'm just looking at the value of n. And if I'm looking at orbitals which are real, 1s, 2p, and 4s are all real. 2d is fake because 2d is saying n equals 2, L equals 2, D is L equals 2, and we can't have that. Alright, so how many total electrons can have a value of n equals 4? So we're going to break down our rules a little bit further here. So for every m sub L number you have, you can make this little box. In this little box, you can put 2 electrons. So for every m sub L level you can have 2 electrons. So if we just look at the n equals 1 level, the only L value you can have is if n equals 1 is L equals 0. Therefore, the only m sub L value you can have is also 0. And since you only have one m sub L value, you can only have 2 electrons. Alright, moving up to n equals 4. Here I have 3 L values. L is 0, 1, 2, and minus 3. Now here's a subtle point not a lot of people get the first time around. You can have, for every value of L you have to specify those m sub L values. So n is 4, L could be 0, and if L is 0, m sub L has to be 0. That's one box. Well, if n is 4, L is 1, m sub L could have 3 values, negative 1, 0, and plus 1. Notice you can have m sub 0 listed twice and they're separate, so in total you would have 4 boxes here. And you do that for L equals 2 and then L equals 3. And what you're really doing is you're just counting the number of m sub L values you have and you multiply it by 2, because each m sub L value can have 2 electrons. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have 16 m sub L values. Multiply that by 2 electrons, you have in total 32 electrons that can have an n equals 4. Alright, calculate the wavelength of light emitted when an electron moves from different energy levels. So when you are going to different energy levels, you have to absorb energy to do that. And usually you do that in the form of light. Not always, but you're going to absorb some kind of light. And we have an equation that tells us, okay, based on the energy level you ended at and where you started from, I can tell you the wavelength of light it took to make that jump. So that's what we're working on here, getting used to this equation. So what I did here is that I wrote out the math for question 5a. So our equation is hc divided by lambda. Lambda is our wavelength. H is Planck's constant. C is the speed of light. Equals 2.18 times 10 to the minus 18th. Multiplied 1 minus n final squared. That's where we end up at. Minus 1 divided by n initial squared. That's what we started up at. So I'm filling in my variables. I'm solving for lambda. Final is 3, so that's 3 squared. Initial is 4, so that's 4 squared. And when I do all the math on the right side of the equation, I get 1.99 times 10 to the 25 divided by lambda equals 1.06 times 10 to the minus 19. Now I want to solve for lambda, so I multiply each side by lambda. Then I can divide each side by 1.06 times 10 to the minus 19. And what you get is 1.88 times 10 to the minus 6. And you should do that for B, C, and D as well, so we can get used to using this equation. And the question is, rank these energies from small to big. Well, your smallest is 6 to 5, followed by a 5 to 4, then 4 to 3, and 5 to 1. And our trends is best showed in this image. So it's cut off here, but this says n equals 1 and n equals 2. As you get into higher energy levels, the gap between the energy levels becomes smaller and smaller. So if we look at the gap between n equals 1 and n equals 2, it's huge. We look at the gap between n equals 2 and n equals 3, it is much smaller. N equals 3 to n equals 4, it's even smaller. So as you go higher up, it's easier, it takes less energy to jump these different gaps. So N6 and N5 is our highest energy levels, and we're only changing one energy level, so that's the easiest to do. And what that means, it takes a less energy to do that jump, so that energy would be the smallest. Question 6 is using this equation again, but this time I'm solving for n final. I know my initial, I want to know where we finally go to, and we're given lambda. So for lambda, I give it to you in nanometers. You have to put it in meters to use this equation. So let's set up our equation. So hc divided by lambda, which I have right here, equals 2.18 times 10 to the minus 18th multiplied by 1 divided by n final, that's what I'm looking for, minus 1 divided by n initial, and initial is 8. So what I did here from here to here is I multiplied and divided everything on the left, then I divided each side of the equation by 2.18 times 10 to the minus 18th. And I get 0.2135 equals n minus final squared divided by n divided by 64. That 64 came from doing 8 squared. Add 1 divided by 64 to each side, I get 0.250 equals 1 divided n final squared. Now, I don't want 1 divided by n final squared, I want n final squared. So what you can do is shown over here, and this is very tricky in all types of math. I want my variable to be not in the denominator but in the numerator, so if I flip each side of the equation, I can do that. So 1 divided by 0.250 equals n final squared is the same thing as saying 0.250 equals 1 divided by n final squared. So 1 divided by 0.250 is 4 equals n final squared. Take the square root of each side, your final energy level is 2. And with that, that's the end of this video. I hope to see you in the next one.